Welcome to the Digital Enterprise Society podcast, addressing all aspects of the digital enterprise, inspiring connection without boundaries and creation without limits. Thank you for tuning in. Here are your hosts, Thom Singer and Craig Brown.
Hey, everybody, and welcome to the Digital Enterprise Society podcast. Thank you so much for picking this show. You know, I know that there are a lot of podcasts out there, no matter what you're interested in. And yet, every single week, many of you find your way back to this little show that we created to be a resource for those who work in and around PLM. The Digital Enterprise Society is a forum for the exchange of ideas surrounding the tools, processes, and practices used across the product lifecycle. To learn more, go check out the website at digitalenterprisesociety.org. My name is Thom Singer, and I have the honor to co-host this show every single week with Craig Brown. He is an industry veteran and former PLM leader at General Motors, but today we're switching this around, and Craig is the guest on the show. You see, Craig, in addition to being the co-host of this show, Craig is early into his career as a retiree. And as I tell him all the time, he's failing at retirement because he keeps working on projects that interest him and that keep him excited about things that are going on in this world. He does some consulting for a variety of small companies, but he also gets involved with big things impacting the industry that really excite him. You see, engineers don't die. They just find new projects to work on. So Craig, welcome to the show as a guest.
Well, thanks, Tom. And yeah, I like this because I don't have near as much prep work.
But I did. Yeah, and I don't like having the prep work, Craig. I'm the high energy introduction guy. So now I got to keep up with you. But Craig, you know, you're here almost every week. Sometimes I do these solo episodes with business leaders and consultants about career stuff, but almost every week you and I are here together. But I'm not sure that everyone who's listening really knows the background of Craig Brown. I always talk about how you used to be the PLM leader at General Motors, but you've done a lot more than that. So take a moment and give us a little overview of your career.
Well, I went to school as an aerospace engineer and came out at a time when I really wanted to work for NASA, and I got into flight controls. So that's how I knew about computers inside of products. And then along the way, realized that the car businesses, so this is a few decades ago, the car businesses were putting more and more computers in cars, and just my own makeup, and also moving back to the Midwest, which is where we were from. We moved back from the East Coast to the Midwest, and I started helping the car companies, especially General Motors, start using more and more control computers inside their cars. Now, I wasn't the only guy. There was lots of guys, but the company I worked with, they had been working with General Motors in space programs, actually. This is a long time ago. And that's how they knew each other. So that's how I got back to the Midwest. And then I did that for a few years, a little over a decade. And then parts of General Motors decided to insource the creation of this control software. And so I switched and joined General Motors directly. And then as careers go, I got challenged with other things at GM. The first was simulation methods, because that's my aerospace background. And then bridging the controls development. So this is the thing that controls your car when you push the accelerator these days. Or if you talk about autonomous vehicles, it's the thing that'll let it be a robot and you just go along for the ride. So those are the seeds of my interest in this general problem of well, how do you do this with virtual tools, computer-based tools, and so on. Anyways, my last assignment, which you know because you tell them every week, was the PLM leader, which is much broader than just simulation, and it was much broader than just controls because it included all kinds of parts in the car and the interface to manufacturing and service.
And during that time, you got really involved with all things PLM, and you got really involved with PLM World. You served on the board for many years. So I always ask many of our guests who have been involved with a variety of industry organizations, why, when you made that move over to being PLM leader, why did you get so involved with now the Digital Enterprise Society, back then was PLM World? Why did you get so involved with the industry sort of think tanks, et cetera?
Well, that's a good question. Part of it was frustration. What bothered me about what a sales guy or what a company would claim is that they had the best solution for, and this is a sales guy talking, right? So they had the best solution for something. And I'm like, well, we already do that this way. And as far as I can tell, we do it better. So why would I embrace your solution? So those kind of frustrations led to, I think it was actually our IT director. They invited me to do a keynote speech. It's where you and I first met each other. And then I learned you were driving well, never mind. We won't go there.
No, I think the world should know that you, when we first met, you worked for General Motors and I had just purchased a Ford Mustang, which I still have and still love.
And what did I introduce at that conference? I introduced it in an audio track of the new Camaro. and so whatever. So I got invited to give that keynote. For me personally, it was, for those of you listening that were there, it was a lot of fun because the morning keynote was, you remember who that was? It was Gene Cernan. It was the last astronaut to walk on the moon. I
do remember that because I got to have breakfast with him because part of his keynote was I sat down and interviewed him on the stage. And for me, that was a huge honor that I got to have breakfast and then interview the last man to walk on the moon. And then it was just, a couple of years later that he passed away. So I do remember that as one of my sort of a highlight of my career, actually.
Well, and in a way, it's a highlight for me because, I'm an aerospace guy. I wanted to work on the space program. And here I am in the same day and the same stage. He was in the morning. I was the last, speech of the day. And of course, I'm talking about computer-based everything. But if it weren't for the space program, we'd have never done it. Right?
Of course, it turns out introducing Craig Brown was actually more important because who would have known that day that we would then be hosting the shows for coming up into our third year?
Well, for you and I, yeah. So anyways, I got to do the keynote. I wanted to emphasize things that I had already talked. You remember the gentleman from Siemens? His name is Jan Lurden. He's from Belgium. And Jan and I had gotten to know each other a few years earlier, before Siemens had acquired him. And it turned out they had acquired, LMS had acquired a small simulation company, which we used a lot inside of General Motors for hydraulic simulation. So, it's just the way things happen. And you were asking kind of this career, what was your motivation? Well, I didn't know Jan until he introduced himself because he was interested in Imagine. And then this whole notion about the soundtrack of the new Camaro, and we used his tools, both his laboratory tools and his simulation tools, in order to craft that sound. It's just an interesting way to remind the audience that, we all talk about model-based system engineering and digital twins. We're already doing parts of it. It's just not in the mainstream of the discussion. Well, here we are in 2021, and it is in the mainstream. And I want to push, frankly, everybody a little further. And that was the point of the webinar I did about, well, if we got a digital twin and we got PLM and we got all these measurements we're making, couldn't we make our products safer? And I think people are surprised when people like me make those statements. They're like, what do you mean by safer? Well, let me explain. And so that was what the webinar was about. And I got a few more of these things that are on my mind. And before I run out of energy, I'll probably do a few more webinars like that. And that'll lead to a podcast with you about, well, why should people care? Well, I hope I get in the next 20 minutes, I'll get that across. So,
well, that's what we were thinking is that, the work you did on the webinar that you did for SimData on this whole idea of making products safer with digital twin. Some people might shrug their shoulders and be like, how does that make it safer? Or aren't products already safe? So why don't you tell us about the webinar and give us an overview of what your sort of thesis was for that webinar, and then we'll dive a little deeper.
Okay. Well, so simulation is great. It can replace physical testing. Sometimes you're limited by physical testing in what you can measure. Literally, where can you put the sensor? You don't have that problem in simulation because it's a virtual world. You can put an imaginary sensor down deep inside of a device, even in the middle of the device, if you think about it, and measure stresses. And so the fact that we're running a simulation and we have this freedom to put sensors anywhere, and think virtual sensors for a second, then that lets me get insights into how a model will behave based on physical principles that I understand. But you still need to get physical measurements to just make sure you didn't miss something, right? We make approximations in all these simulations, and the approximations can sometimes create a blind spot that we think we know, but we don't really know. And that's where field failures or failures in product being used. When I say field, I mean you and I as consumers using a product. That's where failures are. A quality guy would call it a bud of a problem, right? There's some other design flaw, and it's usually, to be fair to the designer, it's usually not a design flaw as much as it is a gap in knowledge. So people didn't know that load case was going to matter. And so a load case is how the product, whether it's a bottle or whether it's a car, how it experiences loads, and so how it deforms when you press on it like a bottle, or in the case of a car, if you crash it. So great. So I can simulate more. I can put in a sensor in other places, and then I can correlate back to physical tests. How would this lead to safer products? Well, you get to this notion of exploring, and I like the notion of exploring because it's discovery, right? You're trying to discover what you don't yet know. So if you're walking across terrain that doesn't have any trails, you're trying to discover, higher ground so you can get a view, or lower ground so you can get some water, right? So in engineering, especially failure engineering, you're trying to understand things that are known unknowns. And I think this is the engineers that build robust products, when they get really good at it, they know the unknowns pretty well. And when they have an area they're not sure about, like maybe a new material, well, then they build in a safety margin. And so when I came through college in the 70s, we were taught, especially for structural dynamics and things like that, safety margins. When we were doing spacecraft controls, we were taught, make sure you have safety margins, even though you don't have an atmosphere screwing up drag. You'd still have a lot of unknowns, like there's an asteroid that just hit your solar panel. That what happened on the Apollo 13 was a unknown condition, and then they had to react very quickly to bring the astronauts back. So this notion of known unknowns and using simulation to build confidence that your design is going to make it, that's the power of simulation. And by the way, it's really compute intensive. It takes a lot of computer horsepower. Thanks to Moore's law, you got more computer horsepower in your cell phone today that can do simulations like this. So it's all become a commodity. So simulating a lot more is fine.
So I like this term, known unknown, but not being an engineer, this is foreign to me. Can you go a little deeper about this whole idea behind a known unknown and why it's so important?
Well, you recently had a power outage, and at the moment that happened, it was an unknown. You're like, what the heck? I got a podcast to do, or whatever else, right?
Yeah, we just to let everybody in, we were supposed to record this yesterday, and my neighborhood lost power mysteriously from some worker cutting a line at about noon. So we didn't know.
And that's the known, right? The known is the worker cut the line. The question that, as a consumer or even his boss, they might want to know is, well, how the heck did that happen? That shouldn't have happened, right? That should be impossible. Did you not scan for the line, or what? I know, of course, it happens now and then, and it's just life. But a known unknown is he cut that line probably because he didn't do a scan of where that line was in the ground, right? So it was an unknown that should have been known, and that's the idea. Well, apply that to every engineering challenge, right? Why did your car fender break a certain way? Why can't we design it to break a different way? There's an example in the car companies today called, and it's actually a regulation in Europe and now everywhere else, I think. It's called pedestrian protection. So your front end and the side fenders toward the front wheels have to cushion the blow to a pedestrian so the pedestrian can survive. And that's like, oh, well, how do you do that? Well, you don't put a big piece of metal out there like we used to do, because that'll just break their legs off, and right, depending on the speed. But if you had something like a pillow, in effect, a pillow, so think plastic fenders that deform, because that's really the way it's implemented. But you still need enough structural integrity so that the car can still protect the driver, right? So these are trade-offs. And to figure this out, pedestrian protection, it had to become much better known what the unknowns were. And, part of that was understanding how legs break, or literally, and then designing panels to absorb energy. So maybe those are two extreme examples, from I cut a wire in the ground that I shouldn't have, to, there's a new regulation, so I better go study not how the car deforms, but rather how the object you're hitting deforms and how do you make it safer.
But Craig, this does sound like a lot of work. I mean, it sounds like there's a lot of study, a lot of measurement, a lot of sort of unpacking that goes on. Isn't that really time consuming and really expensive if we're going to do that for everything?
When it's physical testing, it absolutely is. And this is the opportunity, right? Is because when it's a simulation world, when it's a augmented reality world, when it's, like the movie Avatar, I mean, a lot of times we're motivated by what we see on the movie screens. But remember how those guys were interacting with a 3D hologram and trying to understand. By the way, that's in lots of movies. But this is the same thing now. Digital computers, the ability to simulate what-if scenarios has become so cheap. I mean, any of you guys out there that are, and ladies too, that are gamers, this whole virtual reality world is a form of a digital twin running simulations. So my fundamental point about your question now is it has become cheap, and therefore we should do it. It used to be really expensive and in some cases impossible. The idea of, well, what if I want to measure the temperature inside of the hunk of metal to see if that's what's causing the problem? I had to drill a hole, which then made it kind of different. And then I had to put a thermistor in there. Well, I can do the virtual sensor quite easily. I just imagine it and it can happen, right? So it's just really different how it works. So it's affordable. That's why now.
So your whole claim is that all of this world of digital twin and PLM can help make products safer. What else do we need to know to be able to support that claim?
Well, one of the problems with simulation is you can fool yourself in no time, right? You can convince yourself that you understand something really well, and yet you're getting field data measurements from customers that doesn't match it. And so it's still important to consider the pile of measured data. And this is where the Internet of Things, you've heard people talk about this, or we've had some guests on the show about industrial Internet of Things. And what they're really saying is we can sense more now what's happening on a manufacturing line. Your phone senses now your walking habits, your exercise habits. If you got a Fitbit, it's sensing your heart rate and maybe even blood chemistry. And some of them now, it's kind of interesting. So the fact that we're sensing more data gives us the opportunity to make our models better. And then if the models are better, well, then that makes even more credibility to this argument that a digital twin that includes the simulation can just help you explore safety. So we should take advantage of the data. IoT is now here too. So computing power is great and cheap. We're getting insights of data from everywhere. We got to organize it. It's complicated to organize it. There's this new field that really isn't new, but it's popular on data scientists. And so being able to process the measurement pile, finding the gold, right? It's like taking a magnet to a haystack and looking for the needles. Well, even when you find the needles, then what do you do with them? Well, it would help if you knew how they got there or what are the possibilities. Simulation lets you go backwards in time too. You can imagine, okay, well, here was the failure. What would have caused that? Let's go explore this notion of what causes that type of failure. And so you can run the clock backwards, right? You don't just have to measure and then try to recreate and do it again. Instead, you can take the failure and work backwards. What's possible? And that's based on your knowledge. So open your mind to more measurement, faster simulation, and oh, by the way, you can run the clock backwards. And people have done this forever. Well, not forever. In my lifetime, they've done it. We did it for sure in spacecraft controls, where we would run it forward and then we'd run it backwards to try and figure out what went wrong. And I think this technique of engineering, it'll just get used by everybody. I hope, I think people will get it. Why am I speaking about it so passionately? Well, I really don't care for the sales pitch that says, hey, I got a digital twin, your business will improve. Well, how will it improve? Right? And so I'm trying to give you a better example of it. Hey, I make safer products. Let's talk about it.
So when you presented the webinar a while back, was there anything else that you covered that the people listening to this podcast should know about this whole concept of safety around PLM, digital twin, et cetera?
Well, I think when people think about the quality of a product, so we talked earlier about, well, products are already really safe. Well, of course they are, because you don't stay in business if they're not safe, right? But making them even safer, there'll be this concern about, well, what does it cost me? I also believe that the way we do quality management will evolve. And so quality management historically has been driven by Henry Ford and the mass production line. It's all about build the same thing consistently. And when you don't build it consistently, figure out how to remove that variation, change the line, change the work instructions, change the work habits, something, right? Quality management now, with this ability to explore the known unknowns, is a dimension that needs to expand. And I choose the quality management guys because they have the skills to take these anomalies, we like to call them, these surprises, and go figure out what already went wrong, like your power cable getting disconnected, or people being injured in a crash because the car was really good for the driver to protect them, but really terrible for the pedestrian, right? So the quality people have the right mindset and the right skills, and I think their function in a company will change. And I think this is important because the complex products we all get, so the phone is easier to understand. So let's talk about that for a second. You're getting an upgrade sometimes daily, certainly weekly. And part of the upgrade is security. So a form of safety, right? Because there's evil forces out there and they're all trying to cyber hack your boxes. But you're also getting upgrades for new features. All right. So this validation idea that we got to drive a car millions of miles before we mass produce it. What does that mean when we change an application? Did we actually use it for thousands of hours before we released it? Well, if you're releasing every week, I doubt it. So how did they do that? Well, they do it through incremental processes, continuous validation. We've had a few guests talk about agile development. And it's this principle of continually testing, continually checking with the customer or a subset of the customers that the thing works as intended. This will happen with validation. As that happens with validation, you'll need these quality guys to be really broad thinking and be comfortable using both physical testing and sampling and also using simulation. There's one last crazy topic, and this is another podcast for another day, and I really didn't do this yet. Well, then should you explore the unknown unknowns? And what the hell is that?
I was going to say, I only understand the known unknown now. What is an unknown unknown?
Yeah. So if your power had been knocked out by that asteroid, right? And that's a whole new problem, right? Because all you can talk about with unknown unknowns is system robustness. In the space shuttle flight controls in the 1980s, and as it was being developed, there's 5 flight control computers. I don't know if it is when they ended, but it was back then. 4 of them had the identical same software. So they all ran the same thing, and they were literally voting, in order to decide what to do with flight controls. What's the 5th one? An alternative way, just in case the flight controls had a flaw in them, so that they could take over if there was a problem. Very interesting stuff. I worked for the company that helped develop part of that. And that redundancy in a car would be really expensive, right? But when we talk about automated vehicles on the road or in a factory for that matter, so any kind of robot, having multiple sensors sensing the same thing, even if they don't sense them at the same accuracy, but so they can compare, well, that just improves your confidence that you're operating safely. So this is just another one of these things that simulation computers both the computer in your device and the computer back in the server farm, they can help you know that your products are safer. And they can even start to build in use cases of, maybe if I live on the coast where the water keeps going up, I should have redundant systems where if I live on a mountaintop and all I worry about is consistent weather, I don't need multiple systems. That's a form of safety, this notion of robustness that people probably will talk more about. And because it'll be cheap, because everything in electronics keeps getting cheaper, it'll be commonplace.
So as we wrap up this interview, let's put this into context for all the Digital Enterprise Society members. Why does this matter for our membership?
Well, when you talk about digital twins, include simulation. When you talk about digital twins and in simulation, include measurements, IoT, and start thinking about how the digital twin is a context that helps you improve your understanding. We have a picture that we use at SimData to talk about the evolution, and it actually comes from a textbook, from data to information to knowledge to wisdom. And to go up that scale of maturity, you need context. A digital twin is a context. And you need understanding, measurements, real life measurements of how things are working. The two combined get you to wisdom. The companies and the members of the DES that get what I'm talking about and think about digital twins this way will help their companies move up that maturity scale on any topic much quicker. And I want young engineers, and for that matter, old engineers, I want you to start thinking this way. How can we apply digital twins, simulations, measured data all the time to improve our understanding? And then as we improve our understanding, that'll absolutely improve products. That's how we're going to get safer and safer products.
Awesome. Well, Craig, thanks for coming on as the guest today.
You're welcome. All you got to do is find the topic I have passion on, and then we can go for hours.
I was just going to say, I've worked with you long enough. I know I have to be careful to keep this to a half hour. I had to rein you back in, but this was a great interview. And I think a lot of people can be inspired by what you talked about today. So thank you so much for being the guest, and we'll see you back here as the co-host next week. So, yep. And for those of you who are listening, make sure that you tune in next week and every week, because Craig and I strive to bring you more thoughts, ideas, and information in and around product lifecycle management. And remember this, the Digital Enterprise Society is the place for the exchange of ideas around digital manufacturing tools. Go check out the website at digitalenterprisesociety.org.
You've been listening to the Digital Enterprise Society podcast. Learn more about what you've heard here today at digitalenterprisesociety.org. Join us again next week for more connection without boundaries and creation without limits.